Let us talk about these type of problems where we are given an array of two types of elements and we need to sort this array. This question is asked in different forms and I have written here three popular forms. The first form is given an array of positives and negatives, you need to put negative first in the sorted array and then all the positives. The order among negatives may change, it does not matter, and the order among positives also may change. For example, if you're given this array 15, minus 3, minus 2, 18, you need to produce an array which has all the negatives first, like minus 3, minus 2, and then all the positives, 15, 18. So this is not the only valid output. The other possible valid output can be where you have different order of negatives and different orders of positives. This is second form of this problem, where we are given an array of even and odd elements, basically integers. We need to segregate even and odd, right? So all the even come first, like 14 and 12, right? And their order does not matter. You can put 12 first and then 14, but even should be together and then all the odd elements. First all even, then all the odd elements. The third form of this problem is you need to sort a binary array. You are given a binary array like 0, 1, 0, 1 and you need to sort it. You need to put all the zeros first and then all the ones. For this particular problem, many of us, when we start solving this problem, we think, okay, it's a very simple problem. What all we need to do is count how many zeros are there, right? And then you can get the count of ones by subtracting the count of zeros from total size. Now what you do is you put, say you have the count of ones as count of zeros at count 0. So you run a loop from 0 to count 0 and you put all the zeros first. Then you run a loop for count ones. Count 1 you can get by subtracting array size minus count 0, right? Then you run a loop from 0 to count 1 minus 1 and then you put all the ones after zeros. See, this solution is fine, but there are certain disadvantages with this solution. The first disadvantage is you are traversing the array multiple times. First you are traversing the array to count how many zeros are there. Then you are traversing the array to put the zeros and then you are traversing the array to put the ones. Basically, if you see, you are traversing the array exactly two times. First to count zeros, then you will put those many zeros, you will traverse some part of the array and then you will traverse the remaining part of the array to put the ones. This is one disadvantage, that your array is being traversed twice. Other disadvantages which we many times forget, that these elements may not be only 0 ones, they can represent an object. For example, 0 represents here an object. Suppose this is an array where you have keys as whether a student has passed the exam or failed the exam. 0 means failed and 1 means passed. Now these keys, they represent actual student objects, and when you sort this array, and if you simply put 0, 0, 0, you are losing the relation with the actual objects. So we need to ensure we use an algorithm which simply does not count and put all the zeros, because these can be actual objects also. So please pause this video now and try to think of a solution that takes an array as input and then sorts the array. You can try solving this problem. We are going to discuss different solutions for this problem, and the same solutions can be used for other two problems also. Let us first talk about a naive solution to solve the problem. The idea is to create a temporary array temp of size n, initialize an index variable I as 0. What are we going to do is, we are going to traverse through our input array and we are going to first put all the negative elements from our input array to temp array. Then we are going to traverse our input array again and we are going to put all the positive elements after the negative elements in the temp array. That's why we are using a variable I which is being shared by both the loops. So we are first putting all the negative elements in the temp array in this loop. In this loop we are putting all the positive elements after the negative elements, because we are using the same index variable I for temporary array, right? We have used I here, we have used I here again. So after these two loops, our temporary array has the required order of elements. All the negatives are first and then all the positives. In the third loop, we are simply copying the temporary array elements back into the original array so that our original array is modified. After the third loop, our original array becomes minus 12, minus 10, 13 and 18. Now this solution requires theta n time, requires theta n auxiliary space, and it does 3 traversals of our input array. You can see that first traversal we are doing here, second traversal we are doing here, and third traversal we are doing here to copy the elements. Now please pause this video and try to think of a solution that works in theta n time, takes theta 1 or big O of 1 auxiliary space and does only one traversal of our input array. You might have guessed the efficient solution now. This problem is mainly a variation of partition function of quicksort. And the solution, the naive solution that we just discussed, it was actually naive partitioning algorithm, right? In the quicksort, we discussed 3 different partitioning algorithms, right? So if you've not seen the quicksort videos, please refer the quicksort videos first. In the naive partitioning algorithm, we were doing 3 traversals, theta and auxiliary space, the same thing we did here. So we can solve this problem efficiently by using either Hoover's partition or Lomuto partition. Both of these partition algorithms, they work in theta n time. They do one traversal of the array and they take theta 1 auxiliary space. So now I am going to write Hoover's partition to solve the problem. Please pause this video and try to write down either Hoover's partition or Lomuto partition yourself. Here is the implementation based on Hoover's partitioning scheme. I've done some minor changes in the actual Hoover partitioning scheme. For example, we are not returning any integer value here because we just want to rearrange the array. We don't want to return any index from this function. So most of the code is similar. We are beginning I from here and j from here, right? And when we begin from here, we consider 0 as a pivot. So we find first element which is greater than 0, right? So we stop our I at this point. And this is what this do while loop does. It first makes I equal to 0. Since it is a do while loop, it will first make I equal to 0. That's why we have initialized it with -1. And it will compare, is it smaller than 0? Yes. It will further increment it and it will stop at 18 because now it's greater than 0, right? Same thing will happen with j. It's a do while loop. It will begin from here. It will continue here because it's greater than 0. It will stop here. So they both stop at the point which the elements which should be swapped with each other, right? And since I is not greater than equal to j, they have not crossed each other. This condition is for checking whether they've crossed each other or not. The elements array I and array j are swapped. So after the first iteration, our array becomes this -12, -10. These two elements are basically swapped, right? So we get this and this. Now if you see, I has come to 1 and j has come to 2. And now we are going to begin our second iteration. So what will happen in the second iteration? I is currently here. This do while loop will run. It will make I here, right? And after I becomes here, it will stop, right? Because this condition will be checked. Array I is actually greater than 0. So it will come out of the do while loop. So I will stop here and j, which was earlier here, right? It will enter into this do while loop and j will stop here because this is smaller than 0, right? And now I and j have crossed each other. I has become greater than j. So we'll fall into this if condition and we'll return. And you can notice that our array has become sorted. It's simple Hoover's partition that we have earlier discussed in detail. And time complexity of Hoover's partition is theta n. This has also been discussed. Auxiliary space is clearly theta 1 and does only one traversal of the array.